Hi there, my name is Ricardo and I'm a member of the research team at Neuroelectrics. In this video, I'll present a study that we've performed that's entitled Montage Optimization and tCS Influence of Optimization Constraints. So the biophysical agent of interaction of tCS with neurons is the electric field that is created in the head when we turn on the tCS device. And depending on the orientation and strength of this electric field, the neurons will respond in a different way. The normal component of the electric field is thought to be particularly important since it is aligned with big pyramidal neurons in the cortex. And depending on this orientation, you can either have excitation or inhibition of the soma of these cells, which explains the acute effects of stimulation on neurons. Now, those parameters like geometry, position, and type of electrodes, as well as the polarity and waveform of the currents, influence the electric field distribution in the head. However, just simply replicating the dose parameters across different subjects does not guarantee that you'll end up with the same electric field distribution in all of the subjects. And this is due to different geometries and electrical properties of the heads of each subject, which will have a crucial impact on the electric field distribution. To overcome this is to employ montage optimization algorithms that take into account these idiosyncratic properties of each subject's heads. These algorithms use as inputs computational head models and target information to determine the ideal dose parameters that have a desired effect on specific target areas. We can employ these algorithms in large-scale projects on a subject-by-subject basis. So for each subject, we build its own computational head model, and based on target info, we use montage optimization algorithms for each of the patient, thus coming up with a specific set of montage parameters for each subject. Now, the objectives of this study are to study how these montage optimization algorithms, when applied in large-scale projects, will affect inter-subject variability of parameters that are related to the spatial distribution of the electric field, as well as determine the influence of optimization constraints on the results of these optimization algorithms, and finally, determine how these approaches compare to more traditional approaches where we use the same montage across different subjects. The population of subjects of this study were children and teenagers with ADHD and ASD participating in the STIPED-EU project. I highly recommend that you follow this link and visit the project's website, where you can find more information about the study, about its objectives, and about the partners participating in this subject. So in this study in particular, we used data from 6 participants of STIPED. And for each of these 6 participants, we collected T1 and T2 structural weighted MRIs. We then processed these MRIs using this pipeline to create computational head models for each of the personalized, for each of the subjects. So the first step of this is to segment the T1 into T2 into different tissues, and then build 3D geometric reconstructions of each of the tissue. The head also has models of the electrodes that we used in this study. In this case, we employed 1 centimeter cylindrical electrodes placed in 64 positions of the 1010 EEG system. The segmentation and head model creation was conducted by the team behind the SimNIP software. We're also partners in this project. And again, I highly recommend that you visit their website for more information about the software. The montage optimization algorithm that we employed here was based on the Stimweaver algorithm that we developed here at Neuroelectrics. This algorithm requires as inputs a computational head model for each subject, as well as target cortical map of the area or areas that we want to stimulate. In this case, the target area is the left dorsolateral prefrontal cortex, or LDLPFC for short. So for each head model, we then calculated the distribution of the electric field in the cortical surface induced by all bipolar montages with one common cathode, in this case CZ. It's possible to show that these distributions can then be linearly summed to calculate the electric field distribution induced by every possible montage that involves these electrodes. For the creation of the target map, we assumed here, for reasons that I have discussed before, that it is a component of the electric field normal to the cortical surface that is responsible for the effects of tCS on the cortical neurons. The target map was then set as a positive value for this component of the electric field in the left dorsolateral prefrontal cortex. And the positive value of the electric field, of the target electric field here, means that the electric field is directed into the cortical surface, and that will lead to an increase in excitability of the soma. Another important parameter that we require is a map of weights, which indicate how strongly the algorithm will enforce the condition imposed in any given area. Weights are scalars between 2 and 10, and for the target area, we set a maximum value of 10. The algorithm then determines the montage that minimizes the least squares difference between the weighted target map and the weighted electric field induced by the montage. The montage is constrained by the total injected current, which we set to 2 milliamps in this case, the maximum current per channel, 1 milliamp, and maximum number of channels. How did we analyze the electric field distribution? Well, to analyze the spatial distribution of the electric field, there's a number of parameters that we can employ. Here we focused on two things. The first one was the average electric field on target. Well, the average value of the normal component of the electric field on target, which is calculated with this expression. And this value is just a good indication of how strongly the electric field couples with the neurons in the target area. The second parameter that we use is called ERNI, or error with respect to no intervention, and is calculated by this complicated looking expression. Basically, this expression is calculating the least squares difference between the weighted electric field induced by the montage and the weighted target electric field. And this is actually the function, or the value that the optimization algorithm minimizes for, and just basically indicates how well the electric field induced by the montage fits to the target electric field. So for each subject, we optimized for the stimulation of the left dorsolateral prefrontal cortex with two different target values of the normal component of the electric field on target, 0.25 and 0.50 volts per meter. We also investigated two different values for the maximum number of channels, 6 or 8. This figure here shows the normal component of the electric field for one of the subjects for the 6-channel montage, and for a target electric field of 0.50 volts per meter on the left and 0.25 volts per meter on the right. Notice how in order to increase the electric field on target, the montage on the left places the cathodes further away from the anodes. This is a common strategy that the algorithm will employ to increase the average electric field on target when it can't increase the current due to the current being limited in this study. We summarized all the data in this plot. The top row shows the surface average of the normal component of the electric field on the target, and the bottom one shows the ERNI scores. And for each plot, we compare the influence of the value of the target electric field, so 0.25 or 0.50 volts per meter, the maximum number of channels, 6 or 8, and we also evaluated each montage not only in the head model for which it was obtained for, but also in every single one of the other head models. And the idea of this is to compare between the performance of personalized montages and non-personalized montages. So, summarizing the results, we found that increasing the target electric field resulted in a statistically significant increase in average electric field on target, as expected. However, this also came at the cost of a higher variability of the results across the subjects. We also found that increasing the maximum number of electrodes from 6 to 8 did not result in significant differences in the ERNI and average electric field on target for both target electric field value groups and type of evaluation, so personalized and non-personalized montages. So 6 channels for this particular target seem to be enough. And differences in average electric field were not found to be significant across evaluation types, so personalized versus non-personalized, but ERNI scores were, which indicate a better fit to the target map. So even though personalized montages don't result by itself on a higher average value of the electric field, they do result in an overall better fit to the target map, which is related to focality or value of the electric field, average value of the electric field in off-target areas, for instance. So to conclude, optimization constraints do influence the outcome of montage optimization algorithms at the group level, and they should be planned carefully in large-scale projects. We are yet to test the influence of other parameters like available electrode positions and current constraints, but they might also play a role and need to be investigated further. So thank you for your interest in our work. Please send us an email with any comments or questions or ideas. Don't forget that we have a poster available with these results that you can also download and read it in more detail. And don't forget to visit us at neurolectures.com for more information about the company. Bye.